of y'all, Assalamu alaikum. And today's classroom, I'm going to talk about the last before section known as, we're going to talk about something called as floating point representation. So this is a section we're going to cover first. Okay, today's classroom, I'm going to talk about floating point representation, and we do have another section known as character codes. The theory sections are there, and then the past paper. So almost we are towards the end of this section. Now, what is floating point? Similarly, we learned something called fixed point representation, and there is something called floating point representation. Now, this floating point representation, they have never tested in your exams. Advanced level, syllabus, okay, they have never tested this section in your papers. But model papers, different term papers have included questions in this part. So there is a pretty much chance of getting into this question. So we can see it by your seniors paper, 23 batch students paper in Maluama. We can guess whether this section is going to be tested or not. But so we are supposed to do that section also. Okay, in computers, we learned on something called positive numbers, 10, 20, 100, 30, 50, 60, all those things. We learned on positive numbers in hexa, we learned positive numbers in octal, we learned positive numbers in binary, and then we also learned on something called fixed point. Okay, we learned on something called fractional numbers. Okay, we learned on positive numbers like 50, 100, 30. Okay, we learned on fractional numbers like 50.45, 100.69. Okay, when the male get fractional numbers, we learned on negative numbers also. Okay, negative 500, negative 37. So positive numbers kara, okay, fractional numbers kara, negative numbers kara. Okay, now this next section about floating point representation is going to be talking about numbers which are in large in size. It can be either positive numbers or it can be either negative numbers, a very large number in size. We are going to talk about those type of numbers. Yes, computer deal with big large numbers. So that is what we call as floating point representation. Floating point representation meaning it is a process of representing a large number in a short form, or a short number, not in a large form, but short form, representing a very big number, very tiny number using a structural method. So that is what we call as floating point. Okay, it is a process of representing a large number or a very tiny number in a simple step or in a simple technique. Okay, that is what we are going to talk about. So can you explain about this large number? Why not? Okay, let me take a number like this. 5 zeros, 5 followed by, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros. It is a very big number. If I convert into binary, I don't know how many digits it will happen. So if it is a very big number in decimal, then think about in binary, it will be a very large number, no? Okay, 1, 2, 4, 1000 vandale 10 bits are there. So bits digits here? There are almost 11 digits are there. Or representing a very tiny number. Okay, representing a very tiny number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is a large number or this is a smaller number. Again, if I'm supposed to convert this 0.5k, there is one decimal. 0.000000005k, can you think about it? It will be a very large number in binary. You are getting the point. Okay, a big number, a very tiny number is difficult to represent in binary. So, okay, when you talk about it takes more memory. When the number represent karandai, it will require more memory in your computer. So it's very pointless, no? So the people from IEEE, it is an institute like Halal certificate, like SLS certificate, ISO certificate, okay, computer-related techniques, computer-related technology. There is standard IEEE, Institute of Electronic Electrical Engineering. Institute of Electrical Engineering. They provide standards. They are the ones they handle Wi-Fi standards. They are the ones they handle Bluetooth standards. What is this Bluetooth standard? Wi-Fi ke liye there is a specific range. They are the one who handles 4G network standards. 4G they are supposed to be in a specific range. It's not to be done because it's harmful for people. Okay, that radiation affects people. So they go with those kinds of ranges. Those standards are provided by IEEE. IEEE came up with a solution to represent this large number or represent this small number using their technique. Okay, that is what we are going to talk about in there. IEEE came up with the technique called as 754. If technique again, they represent 754 standard is representing floating point. Now, how can I represent this large number in a shorter way? You can do it. 5 into 10 to the power what will give me this answer? 10 to the power 1 is 10. 10 to the power 2 is 100. 10 to the power 3 is 1000. So number of zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 5 into 10 to the power 10 equivalent to this number. Okay, rather than representing this big number, it is easier to represent this. This is what floating point represents meaning. Did you understand? Kind of similar. Okay, then what about this? So the decimal place is here. If the decimal place is moving towards this side, it is positive. Okay, maybe many. If the decimal place is moving towards the left side, it is positive. If the decimal place is moving towards the right side, it is negative. So I'm going to take 0.5 into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Minus 10. Did you all get it? Did you all get this? Okay, so same structure of representing a very large number using a simple format or a very tiny number using a simple format is what we call as floating point representation. To support floating point representation, IEEE, Institute of Electrical Engineering, came up with a standard called as IEEE 754 standard. A standard, there are two types of notations. Okay, there are two types of notation. One we call it as single precision, and the second one we call it as double precision. Okay, single precision is for the computers with 32 bits. You might have found 32-bit computing, 32-bit operating system. Double precision is for 64 bits computing. Single precision, double precision. PRECISC. Precision standard. Single standard, double standard. That is where operating system make the number of bits which can handle ones and zeros is 32. Operating system we have the advanced version 62. Okay, later in Windows they were using 32 bits. Now in Windows they are using 64 bits. The more the number of bits, the higher the calculation can do. It's almost similar to where how many words you can talk in a minute. Okay, this computer can perform 2 to the power 32 number of transactions. 2 to the power 32 number of transactions in given instant. So IEEE came up with these two standards: single precision and double precision. Single precision is 32 bits. Double precision is 64 bits. What is the full form of IEEE? Write it with me. Institute of Electrical Engineering. Create standards for communication. Create standard for electronic devices. They are the ones they create Wi-Fi standards. They are the ones they create Bluetooth standards, infrared standards. Okay, another packaging. Okay, radiation, different type of devices. Everything related to electronic device. If you are buying an electronic device, they are supposed to go through with their standard, IEEE standard. 754 standard floating point representation. Single precision, double precision. What is this? We are trying to represent a very large number using a short method or a tiny number in a short method. Advantages: What is the advantage of floating point representation? You save memory. Okay, you can save memory in your computer. You don't need to use much memory. So floating point representation memory save memory. So you don't need to spend so much of memory of storing a large number, but in short way. When you represent a number in this way, in an IEEE standard, you come across a number like this. Let me take 732 into 10 to the power 5. When the you are going to represent the number. Okay, it was IEEE standard. If I want to make it, some parts are there. This plus or minus we call it as the significant. Significant T danda significant D danda 2. May decimal point being a radix point. Okay, and this is the base. This is the exponent. Okay, and this is this integer part, and this is the fractional part, fractional portion. In IT, you also can learn fractional portion is also known as mantissa. These are the component of an IEEE. This is a component of an components of components of floating point format. So you have plus or minus, we call it the significant or significant T danda through D danda through. Okay, integer is that 5. The decimal point is the radix. Okay, 732 is the fractional part. O mantissa. Okay, 10 is the base, 5 is the exponent. Exponent, not the power. Okay, so you can say this way. Fractional part, O, you can say it as mantissa. Exponent, O, power. Make your note that then, but more than my note, whatever you are writing right now is the most important part. Okay, whatever you are writing right now is the most important section. So make sure you complete it also. So, single precision so it has a format. Okay, IEEE 754 single precision, that is a single precision standard. Okay, single precision standard. Okay, it has the format. Single precision standard has 3 components. Okay, your IEEE standard of representing floating point, a large number, has 3 components to be done. Sign, exponent, mantissa. You are supposed to have these 3 points in there: sign, exponent, and mantissa. Okay, sign, exponent, and mantissa. Sign, it has 32 bits. So let us see how this 32 bits is allocated. 1 is a bit, 0, 1 is a bit. So sign nekata you use 1 bit, exponent nekata 11 bits. So here you have 9, 32 minus 9. Yeah, 30 minus 9 is 21, plus 2, 21, 22, 23. So here you will have 23 bits for the exponents. Got it? Okay, again, your answer should be 32 bits. Well, it can be 100 digits, it can be 1000 digits. You're going to reduce that 100 digits or 1000 digits into just 32 bits. Okay, in that 32 bit, first bit will be the sign. As I told you, there is a significant. Okay, significant, okay, or significant. Exponent, the power. Okay, and I have written exponent again. Sorry, it should be the mantissa. right? So here you will have the Manthisa. I have written the exponent again. Okay, so here this single precision will have a Manthisa here. So 32 bits is used for the Manthisa. This was the structure, it's standard structure. Right? You will learn it in there how this standard instruction goes on. Right. Then we do have 64 bits. Double precision. Okay, double precision. How many bits are allocated for double precision? 64 bits. Okay, again, if you're going to represent, it can be 1000 digits. You can represent that 1000 digits in just 64 bits. Okay, here also you have the sign, okay, exponents, Manthisa. Okay, sign they allocate 1 bit. Exponent they allocate 11 bits. So 11 plus 1 is 12. Okay, total you have 64 bits. 64 minus 12. Is it 52? 52, 53, 54. Yeah, 52 bits. Okay, 52 bits are used for the Manthisa. 1010 52 came. So in A level, we will be learning only single precision. Right? Copied on this also. That is IEEE 754 format. Heading IEEE 754 format. Single precision, double precision, 32 bit, 64 bit, minimum structure. Okay, single precision. Yes, someone was asking me what is precision. Single precision. 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 Single precision. If the IEEE format has 64 bit, it is double precision. If the IEEE has 32 bit, it's double single precision. So the bits on the sir, the 1 0 1 0 1 0 1 0 1 0 is the name. Okay, 32 bits are involved. Single precision, double precision, 10 bits. Maybe 32 bits, maybe 64 bits are supposed to have it. Okay, then, okay, we come across how to represent, okay, or else rules for normalization. Normalization we can't represent as we want it. Okay, this is called as how to represent IEEE format, IEEE 754. Kohamada make copy represent karande, and there are certain rules are there in order to normalize, in order to solve it. The first rule is, okay, any number must be converted into binary. First thing that you're supposed to do it is, any number you convert it to binary. Okay, you're supposed to convert it to binary. Second one, okay, follow the integer part. Okay, or represent the integer part. Okay, represent the integer part as, not follow, we'll say represent integer part as. Okay, can you then integer part tag in there was a student, they asked me, so what about the integer part? Okay, you are supposed to represent the integer part as 1 point anything. Okay, so if you convert it into binary, you will get only 1 0 1 zeros now. So in there, make the representation as 1 point anything, not 0 point something, 1 point anything. For an example, so I got this expression. Okay, example I can do that. Example, let's say you got this expression. Okay, representation. So if you do the normalization, it will be 1.0111. Right? We are getting the decimal point here. It should be 1 point anything. Okay. Third step is IEEE structure. Okay, IEEE structure. Sine, exponent, mantissa. IEEE structure. First thing is convert any number into binary. Represent the integer part as 1 point anything. For an example, if I have 1010.11, you should convert it as 1 point anything. So if I have 1 point something, it should be not going to convert it. It should be converted to 1 point anything. So if you have it 1 point anything, just keep it as it is. Then IEEE structure is a sine, exponent, mantissa. Okay. Then fourth one, calculate Bayes exponent. Calculate Bayes exponent. BIASED exponent. So what is Bayes exponent? I'll come for it. When I'm teaching you, I'll explain you. Fourth one, representing IEEE format. Representing IEEE format. Okay. Step number 1. In order to solve, in order to calculate, in order to generate, in order to convert a big number in structure, you will be following these steps. Number 1, any number should be converted into binary. Number 2, represent it in integer format as 1 point anything. If I have 101.11, it will be 1.0111. Third step, follow the structure. IEEE structure, sine, exponent, mantissa. Fourth one is calculate the Bayes exponent, BIASED exponent. Okay, you will learn something called Bayes exponent. Fourth one, representing IEEE format. So these steps you will be following up and learning to do. Okay, shall we go for the next part? You'll copy it down. So let us convert this number. We'll convert a number in there. Okay, any number should be converted into binary. So that's the first rule in that. Fifth one is representing IEEE format. Okay, let us convert a large number into an IEEE format. Okay, let us do it like this. I'll go with a story so it will be easy for you all to understand. Okay, now let us take this computer. Let me take our CPU. Okay, right. This is our CPU. Okay, we do have the chip here. The IC is available. IC, integrated circuit, the chip. Okay, when me IC can generate venava. Okay, when me IC can generate venava. Okay, this IC is being connected to this CPU. Let's say. Okay, this IC generates a large number. When you do a calculation, it generated a very much large number out there. For an example, like 1101.1110000. Okay, 1010. When the large number generated, okay, your IC integrated circuit generated a large. This is not a large number. Generated a large number. Okay, when this IC generated a large number inside the IC, okay, what will happen is it will represent, okay, the value in IEEE representation. Okay, and it will represent and provide it to the CPU. So rather than providing the bigger number, it will reduce it into an expression of 32 bits and generate it. This IEEE format can be happening inside the IC or it can be done by the firmware. Okay, firmware ROM does this task. Okay, rather than sending CPU can only understand 32 bits. We generated a number with 100 bits, 100 ones and zeros. IEEE will convert this 100 ones and zeros just into 32 bits. We are going to do it in that way. Okay, so that is what we are going to do. Did you all understand? IC generated large number, CPU understand only 32 bits. So the firmware will convert this larger number into this 32 bit. IEEE 754 precision. Did you get it? IC circuit generated a larger number, computer understands only 32 bits. So the firmware, where the hardware and the software together, it can be the ROM, converts that larger number into an IEEE format. Okay, convert that into an IEEE format. We're going to make it a story. Okay, now we are going to do at that work. We are going to be that firmware, we are going to convert it. So, sir, let's assume that this IEEE format selects single precision. Okay, let's assume that this IEEE format selected single precision, 32 bits. Okay, in normalization, the first rule is any number should be converted into binary. Boom, we have the first number as binary. So we don't need to do the first step. We have eliminated the first step. Any number should be converted into binary. Done and dusted. What is the second step? Convert the number, binary number, as 1 point something. Convert the integer part as 1 point anything. Because why? When you convert all the numbers into 1 point something, it's common, no? So you can eliminate that integer part. Someone asked me this question, sir, in sine, exponent, mantissa, don't we have the integer? We can eliminate integer. Why? Every IEEE number will have 1 point something. So how can you get this 1 point something keyword? This should be taken here. So you're moving towards the left side. Is it left for you? For me, it's left. Okay, left side, it is positive. Right side, negative power. So the number will be 1.1001. 1, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 0, 1, 0. Into, we are doing binary, 2 to the power base. 2 to the power how much? 2 to the power what? Can you say me? It is a positive number, so it is a positive number. 2 to the power how much? 1, 2, 3, 4. Awesome, good. 2 to the power 4. If you are moving the decimal place this side, left side, it's positive. Right side for a negative. Yeah? Done. So next we do have to put it into IEEE format. I also gave it. Okay. Next one is the IEEE value. IEEE 754 standard. So first we do have the sign, then we do have the exponent. You don't need to put a box, but I'm just putting it off just to show it here. So what is the first thing you will have? Sign, exponent, mantissa. Right. Okay, mantissa is the fractional part. Copy and paste it. Right? Mantissa is the fractional part, no? Can you remember fractional part of mantissa? Make a copy. 1, 0, 0. 1, 1, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0. But there is a problem. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Mantissa has how many bits? How many bits are there? 22, 23. 1, 11, 11, 11, 13. 1, 8. 22. 23, no, yeah, 23. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Add zeros to make it in there. Okay, just add zeros in there. Just add zeros. Okay, it is the mantissa. We are going to add zeros to the right side. That is the mantissa. We add zeros to make sure that it has 32 bits. You can ask me a question. So adding 0, will it not change the value? It won't change the value. Okay, because 0.5 is equivalent to 0.52 zeros, 3 zeros. Fractional part is zeros at clear? Okay, 0.5 and this both are equal, right? Okay, in fractional part, the place is the most important part. May zeros doesn't have a value. So did you get it? Make it there, brother. So what do you understand here? Okay, 32-bit take, what did you do here? We convert into exponent. So then the sign. Sign is very interesting. Sign is similar to our MSB, LSB. Okay, main sign negative. This sign, if you are representing a positive number, or if you are representing a negative number, sign will be as follows. If it's a positive number, or if it's a negative number. According to this question, we are representing a positive value. According to this representation, we are representing a positive value. So if it's a positive value, the sign will become 0. If it's a negative value, the sign will become 1. A family 1 to you. Okay, since we are representing a positive number, the sign will be 0. Okay, what about the exponent? Exponent is 4. Okay, now my question is, exponent can it be negative number? Can this exponent be a negative number, or is it always positive? Can it be a negative number? Okay, yes, it can be. No, if you move the decimal place toward the right side, it is negative. If you move the decimal place toward the left side, it is positive. So this exponent can be negative or positive. What if it's a negative number? That's very thoroughly. 1's complement, 2's complement, sign magnitude as well. See, if it's a negative number, we don't know how to represent it. No, whether should I represent in 1's complement, whether should I represent in 2's complement, or whether should I represent in sign magnitude. It's a problem. So we come across something called as Bayer's exponent. Okay, Bayer's exponent is where you get rid of non-negative values. You get rid of negative values. Exponent will be added with a constant to eliminate negative value. Bayer's exponent is where it will be added with a constant value to eliminate negative value exponent. Why? Because 4 can be represented here easily, but -4 problematic situation. No, should I put sign magnitude? Should I put 2's complement? Should I put 1's complement? Did you get the point? Okay, negative number of because we don't know what representation. If 1 0 1 0 put I have to -1. So okay, Bayer's exponent comes in there. Bayer's exponent will be added with a constant. Your exponent will be added with a constant to remove non-negative values. To remove negative values. Okay, your exponent will be added with a constant. Exponent will be added with a constant. Okay, your exponent will be added with a constant to eliminate the non-negative values. Did you get that point? Okay, so if you add with a constant, the negative number, suppose if you get a negative number, will be eliminated. So your exponent is 4. Your exponent is 4 should be added with a constant. To get the Bayer's constant, we have an equation. 2k minus 1 minus 1. K is the number of bits. K represents the number of bits. Okay, here K represents the number of bits. Where should I write it? K is the number of bits. Where can I write it? What may give a number? 4 will be added with 2 to the power. How many bits are allocated for the exponent? K. K is the number of bits. K. 8 minus 1 minus 1. 4 plus 2 to the power 8 minus 1 is 2 to the power 7. 2 to the power 7 is 128 minus 1. 4 plus 127, that is equal to 131. So this is our biased exponents. If you do this 2 to the power k minus 1, any negative number, okay, if you have any negative number, it will be eliminated. Okay, so that is the main thing in biased. Biased will remove negative numbers. Okay, if you have a negative exponent, it will be removed. Okay, using this method. So 131. Convert 131 into binary. Okay, that is 128 plus 3, no? 128, 128, 3, 1, 1, 1, 2, 4, 8, 16, 32, 64, 1, 2. This is the answer in IEEE 754 representation. So this number is represented here.